This episode is sponsored by Brilliant. The universe has been around for billions of years, yet we've only been studying it for a few centuries. Who knows what secrets it still keeps, and what strange technologies we might develop as we discover those. So today's topic is Clarketech, a term we use on this channel for referring to technologies that generally operate outside the bounds of known physics. We've a lot of material to cover, so you might want to grab a drink and a snack, possibly a slice of pie. We get this concept of Clarketech from a trio of adages by science fiction writer Arthur C. Clarke, known as Clarke's Three Laws, particularly the third one. They are 1. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. 2. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. And 3. Any sufficiently advanced technology is indistinguishable from magic. The third one is the most quoted, but as a group they highlight the reason we generally won't say anything is impossible. But this shouldn't be taken too far, and folks tend to fall into a sort of intellectual laziness by constantly asserting anything is possible. We do not constantly change our physical laws and overthrow science, that's a truism, but we are constantly adding to our knowledge and often find weird cases or exceptions, usually minor tweaks or phenomena that become the exceptions that cement the rules. On this channel, we usually try to look at the future under known science, picturing a future where those known rules more or less hold up, to show that we can accomplish many impressive deeds without relying on technologies that would be practically magical to us nowadays. Nonetheless, none of us really expect our current understanding of science to be complete, even ignoring that we have a lot of open questions still to answer. We take as a given that those questions, once answered, will spawn more, and that some of those answers will open some truly game-changing science akin to what special relativity or quantum physics did. Since we don't know what we don't know, this is often a bad approach for contemplating the future. A comment like, "anything is possible," does us little good, since that would not just include things like faster-than-light travel or time travel, but the moon actually being composed of blue cheese, with a thin crust of rock having accumulated on top of it. So Clarketech is not anything is possible, but what might be plausible if something specific in our understanding of the universe turned out different, though we generally include any technology common in science fiction too, like force fields or teleportation. Many of the examples of Clarketech already have well-known names too, and we have covered some of them and will skim them today, especially since we don't just want to mention examples of Clarketech, but talk about their implications on civilization if we had them. There is no way we can possibly cover them all with any depth in a single episode though, so this is fundamentally an overview episode, and we'll add to it as time permits. We will also run a poll over on the community tab of the SFIA YouTube channel with them all listed to see which we'll cover next. Often a technology created in science fiction has all sorts of secondary uses the author didn't think of, which can wreck a lot of the plot when contemplated. And for a lot of these technologies, there are uses folks wouldn't normally think of that are often far more valuable. For instance, this month we are celebrating The Hitchhiker's Guide to the Galaxy as our series for the month, and in that we have the Infinite Improbability Drive, a ship drive that can basically take you anywhere very quickly, but does so by playing with probability in often crazy ways, as the engine warms up to the increasingly improbable. Changing missiles into whales or petunias was one example, as was burying a starving planet in a rain of fried eggs. Playing with luck is a common technology or ability in science fiction and fantasy, I think because the authors know the protagonists constantly bumping into world-changing events and surviving being at the epicenter of them strains plausibility so much. Larry Niven plays with being lucky as an evolved trait in Ringworld and his other known space novels, and Robert Jordan's Wheel of Time series has characters who are Ta'virin, a name given to people who destiny tends to center on, thus explaining their typical heroic properties of stumbling into crises and opportunities and surviving them, but with weird local effects. In a town they are visiting, many things will happen that are possible but improbable, like every coin landing on heads when flipped, or people finding buried coins when they dig a new well, or bad things, like a windstorm knocking free a single roof tile that flies through the air to hit someone on the head and kill them. Now consider this ability to affect probabilities in the context of quantum mechanics, and the various quantum events that, as best as we can tell, are truly random. We know many particles have half-lives, a period of time where there's a 50-50 chance they will decay. They may not, and it would be atypical for one to decay exactly at that time. One with a half-life of 24 hours might decay a second later, or a century later, but if you have trillions of them in one spot, same as flipping coins, a day later almost exactly half of them will have decayed. If you can manipulate those probabilities, you might be able to make it so that half-life changed, or that every coin landed on heads when you flipped a switch. In this case, every particle decayed right at that moment. When playing with luck, we think of surviving the odds, winning the lottery, or getting struck by lightning. We don't think of an amazing and compact power generator where some fairly benign and long-lived radioisotope might, at the flip of a switch, suddenly start decaying very quickly. It can also potentially be used to play with things like fusion too, allowing improbable combinations of smaller elements, or to make stable isotopes, ultra-big atoms that should decay almost instantly but do not. One possible way to create materials in the hypothetical island of stability, very dense elements with far higher atomic numbers than uranium that may actually be stable, itself arguably a type of Clarketech. It also makes for a potentially terrifying weapon. Planets tend to have tons of fissile materials at their center, and suns are warped by a constant coin flipping of hydrogen atoms combining to fuse. If you could screw with the probability of that happening even just a little bit, you could potentially blow up either, or go backwards, suppress nuclear reactions to shut off a star, or keep a nuke from detonating. There are plenty of simpler examples from physics as well. The second law of thermodynamics postulates that every closed system proceeds toward a state of higher entropy, but the entropy of a physical state of the system is actually just a measure of its probability. In other words, the highest entropy state of the system is just its most probable one. If you have a closed canister of gas, nothing in physics precludes all the gas molecules from bouncing over to the left side and leaving the right side in a vacuum for a while. It's just an improbable coincidence, far less probable than the state where that gas spreads out evenly, and of course staying in that state for long is far less probable than returning quickly to what we would call the normal state. It's important to understand that the second law of thermodynamics is a probabilistic statement, though statistics pretty much turn into laws when you're looking at Avogadro's number of particles, but even this basic law of physics will fail near an infinite improbability field. These are the kinds of implications such technologies could have that we and authors tend to skip over, focusing instead on just winning at cards or dice a lot. And we have another that leads us into another example of Clarketech too, the perpetual motion machine, since fundamentally entropy is a probability-based process as well. We also shouldn't rule out that if you can play with probability, you can also make things which have a 0% chance or 100% chance so they can occur or don't occur. Since we are speaking about violating the second law of thermodynamics, perpetual motion machines are probably the most prominent technologies that are forbidden by it. Now, a perpetual motion machine is a bit of a blanket term. Most physicists and engineers using the term generally mean anything which violates the laws of thermodynamics, an easy example being a bike wheel that if spun never slows down from air drag and friction, or which actually speeds up. Note that it does not necessarily need to violate conservation of energy to do this. It might, for instance, have some weird property that lets it leach momentum and energy off air particles it hits, cooling them while it speeds up. no new matter or energy is created, just moved in violation of entropy. Such a thing, if invented, has huge implications on many things we discuss here. We often talk about the Fermi paradox here, and something we call the Dyson dilemma, the issue that expanding civilizations ought to want to take advantage of all the matter and energy they can by englobing or disassembling their own sun and any others they encounter. We had some caveats on that, and one of those was perpetual motion machines or other thermodynamics violating devices. This both reduces the need to grab power sources and partially negates the no stealth in space rule, because it's mostly the emitted waste heat that makes it impossible to hide. If you can constantly recycle your energy supply without entropy in the way, then every house just has a magic bike wheel in the basement with a generator attached and is super insulated to not lose heat. This is essentially an eternal setup, immune to the slow decay of the universe. If it conserves energy, you still have to worry about slow losses to leakage, and you still need matter and energy to expand, too. If it doesn't obey conservation of energy, this is a truly eternal setup, because you need not worry about leakage, and you can actually create matter from energy. Matter is just one state of energy after all, and you can convert energy into mass by ripping quark pairs apart. For instance, rip 2 quarks apart, and the energy needed to do that produces 2 new pairs of quarks instead. You can also dump it into black holes, which mostly emit photons as Hawking radiation, but also produce some particles too. But this is where those implications can radically shift our view of the universe. I'm rather notoriously of the opinion that intelligent life is ultra rare. So rare, most galaxies and maybe even most superclusters won't have birthed one yet, precisely because of the reasoning of the Dyson dilemma. Show me a bike wheel that never slows down without an external power input, and I'd instantly have to revise that opinion. By a reverse of that, I tend to assume faster than light travel and time travel, arguably the same things, are impossible because the universe is huge, likely far larger than the observable portion of it, or even infinite, and is still very young. If you can travel from any place or time in the universe to another, it begins getting truly absurd to assume no one has landed here on Earth. The moment a single species emerges with such technology, it can not only colonize the whole of the universe, but go back and colonize it the moment it became livable, or even further back and just tap the super hot and dense era for matter and energy. One and done Fermi paradox examples where it only takes a single example of a behavior to negate a solution are the worst kind. The same applies for traveling between alternate realities, like colonizing empty Earths where humanity hasn't evolved yet, or traveling to parallel universes. You can visit or colonize a lot of places, so making the sum total of reality larger never helps to explain the Great Silence, nor does any technology that allows such travel to be easier. We've covered FTL methods more elsewhere, including the old FTL series, so we'll bypass further discussion, except to note that when we were looking at wormholes, we commented that if you could make the classic portal or gate we see in science fiction, you'd potentially get unexpected uses, like dropping one end of a wormhole into the sun to provide cheap power, or to regenerate stars by siphoning off helium and adding hydrogen, or weaponizing the thing by dumping one end into a star and the other as a giant flamethrower on an enemy's planet. Teleportation, which we discussed in detail last year, offers many of the same options. You can make some very fast and cheap ships if you can teleport or gate in fuel or propellant to a ship, though often one would wonder why you would need spaceships at all, when you can just gate or teleport from world to world. More mundane uses would be people having them in their houses, where doorways lead to other rooms located on different planets or even realities, kitchen on Earth, breakfast nook on Mercury, and so on. This would be handy for storage too. You could have a closet opening to a warehouse somewhere else, or even cabinets or backpacks like that. This brings up the notion of hammer space, named for old cartoons where the character could yank a hammer out of thin air to hit someone on the head. Folks who play Dungeons & Dragons will know it as a bag of holding, and of course the TARDIS from Doctor Who, bigger on the inside than the outside. It could come in a lot of forms, like a box that on the outside was a cube a foot across, but on the inside was a foot wide and long, but a mile deep. This is obviously handy in any civilization with filing drawers, refrigerators, or magazines for guns, since it allows huge and easy storage. It raises the question of if that mass is reduced too, though. Normally the assumption of Hammer space is the mass is being nullified or reduced too, and that has some awesome secondary effects as well. Not just for classic storage, letting you carry all your junk around in your pocket or cram a mansion into a closet. You could store huge amounts of mass in there, which would be a handy way to get around gravitational compaction for building megastructures or fueling ships if your pocket dimension ignored inertial mass. That's an important distinction too. We tend to use mass as a single concept, but we've got three types of mass. Inertial mass, what resists us when we push on something to speed it up. Active gravitational mass, what generates gravity to pull on things. And passive gravitational mass, what is getting pulled on by gravity. One of the mysteries of modern physics is why inertial mass and gravitational mass are the same, but perhaps they don't have to be. The ability to manipulate one or all of these is an entire category of Clarketech. There are also decently plausible options too. Gravity is the first of the four fundamental physical forces we discovered, but also the weakest and arguably the least well understood too. It's entirely possible we might figure out how to generate gravitons or block them from hitting something, an example of anti-gravity, itself one of the best known Clarketechs. This whole area is terribly underexplored in science fiction though, especially considering artificial gravity is ubiquitous in sci-fi. A lot of the interest in playing with mass is with negative mass and matter. It's fairly critical to most hypothetical FTL ship drives, but even just being able to mess with one of these three types of mass, reducing it rather than making it zero or negative, or increasing it, has huge implications. We'll skim those today, but a ship that could drop its inertial mass while maintaining its kinetic energy could flick that on and suddenly leap up to a huge speed, shut it off and drop back down again, totally altering our normal view of ships not being able to stop mid-flight or parking next to each other to exchange fire rather than flying quick passes. It also allows way cheaper and safer spaceflight, since a ship moving at relativistic speeds might not have tons of kinetic energy anymore, expensive energy that also made it a giant weapon for ramming into planets. A similar type of Clarketech is the reactionless drive, and this would be one avenue for producing such a thing or a close approximation. It also rearranges our thinking on megastructures a lot. You don't build big rotating sections because you have artificial gravity, but you also don't need to worry about their size much, since you can resist gravity. No super huge constructs collapsing under their own weight. You can also go the flip side and increase gravity, potentially allowing microstars, local areas low on mass but high on gravity where fusion could ignite easily, or where micro black holes could be easily formed. Of course, we can potentially already do some tricks like this by using dark matter, if we could figure out how to use it, since it interacts with nothing except by gravity, so if you could manipulate it, you could make high gravity regions that were otherwise empty. One possible way of making slow time fields, for instance, since mass slows time, but you can't really put valuable things in such places as it would tend to be ultra hostile there, like a neutron star, wherever you powered enough mass to seriously slow time down. This raises interactions with matter where we normally can't, and dark matter is a great example since its value is that it interacts with virtually nothing, but this makes it hard to use for the same reason. We have materials that can absorb photons and produce electricity, or vice versa, photovoltaics. One could imagine materials that interacted to contain dark matter, or other weakly interacting particles like neutrinos. If you could make a solar panel that converted neutrinos into electricity instead, you'd gain access to a huge amount of power that also wasn't blocked by things like clouds or our planet, the two big problems with normal solar power. Call this photonutrionics, and that would also be handy for communications, no disruptions from walls or such. Parallel technologies might be photogravitics, panels that absorbed light and produced gravity, or the reverse, absorbed gravity and produced photons, which would be very handy for lighting many of those bigger mega-Earths or shell worlds we sometimes discuss building around small or degenerate stars, which are a pain to light normally. If it absorbs light and produces gravity, you might end up with Dyson spheres or swarms where you lived on flat plates absorbing light and producing gravity instead of a classic cylinder habitat. Even very limited improvements in such technologies, like ones that merely reflect light normally, but reflect frequencies we can't really build mirrors for, like gamma rays, would be incredibly handy for things like fusion or Kugelblitz black holes. Indeed, Kugelblitz black holes, which we've discussed extensively here, are mostly Clarketech because of a lack of gamma ray mirrors. Being able to play with the physical laws, or constants directly, is yet another type of Clarketech. We don't know why the various constants like gravity or the speed of light are what they are, unless you subscribe to simulation theory, where those are set by the computer programmer. There may be other universes where they are different. However, we can't rule out that we might be able to alter them locally one day, same as we might be able to play with probability one day as we discussed earlier, and with some overlapping effects too, since a lot of things like nuclear interactions are based on the speed of light or other constants. That's another of the Fermi paradox solutions too, that civilizations might migrate to universes with physical constants that were more optimal, or tuck themselves into pockets of space where they've messed with those. Light lag is a huge problem for any advanced civilization. FTL is often suggested as the solution, but being able to make a pocket of space where the speed of light was just higher, or gravity weaker or stronger, or so on, might solve many of those issues. This isn't just physical constants either. This episode is coming out on Pi Day 3.14, and of course is followed by a lot more digits. Historically, a lot of folks have tried to make it a rational number, though the more extreme stories like Iowa trying to set it to exactly 3 are fictitious or exaggerated. Still, imagine if you could set pi as being exactly equal to 3, or make a circle that had only 359 degrees, or 361, or a box where anything going off the right side emerged on the left, like in some old computer games. You could presumably make a simulated universe where that last one was quite true. Needless to say, building your own universes or being able to simulate them is Clarketech too, especially types of reversible computing that might let you get around how many simulations you can make from available mass and energy. We mentioned having a bike wheel in the basement as a perpetual motion machine running your house for eternity, but you could use the exact same tech to run a huge simulated universe too, benefiting from its entropy-violating ability to let you use the bonuses of cold computation for hyper-efficient computing we discuss in the Civilizations at the End of Time series. You could have your own simulated universes in your basement then, your own virtual worlds, something we discussed a couple months back. Of course, Clarketech that gets around things like the land hour limit or other computing limitations might be on the table too. And we have a lot of Clarketech in that category, though it's worth noting that things like nanotech and utility fog or smart matter, little micro machines that can take any form or quickly construct things for you, probably are not Clarketech, as they operate inside known physics, though more extreme forms that do it faster or at smaller scales, picotech and femtotech, arguably are. See the Santa Claus Machine episode for some of the limitations on speed and microsizing that we'd have to overcome for these technologies, and which are imposed by known physics when we dissect them and look at practical considerations like heat loss, chaos, noise, and the sticky fingers problem. Speaking of computation and chaos, One of the big problems with weather forecasting, let alone any human prediction technology like Isaac Asimov's Psychohistory, is chaos and exponentially increasing needs for processing when forecasting complex systems. So Psychohistory, for instance, would be an example of Clarketech, and one we discussed in its own episode. We have so many more. We haven't even discussed things like building matter out of things other than up and down quarks, like strange, charm, top, or bottom quarks, or creating new types of matter entirely. What about magnetic monopoles or magmatter, or neutronium, or structures built of frozen light or tachyons? We haven't discussed speeding up time. The universe lets you slow time but not speed it up. That would be another Clarketech. We hinted at building pocket universes here with different laws, but what about building pocket universes like ours, but in different universes with different laws, like the webway from Warhammer 40k? What's the effect of such places on the universe, around the edges? Would you get weird boundary or fringe effects, or their own type of event horizon? Could uses of such things be a type of suicide pact technology? Invent time travel and instantly erase your whole civilization when you use it? Could you have places that violated causality? We talk about being able to augment our minds, to be able to learn faster or store memories better, or even transfer memories to others or delete them. But what about a technology that did not delete a memory you found unpleasant, but deleted the event itself? Needless to say, we've only scratched the surface of possible Clarketechs, and the uses and implications of those we've briefly touched on. As mentioned, we will do a poll over on the SFIA YouTube community tab to see which ones we'll do next, either as their own standalone episode, or possibly a few in a single episode or shorter bonus episodes for them. We will also open a poll on our Facebook group, Science and Futurism with Isaac Arthur, where you can suggest your own Clarketech options and discuss the implications of these various techs, and I certainly welcome any thoughts on them there or in our YouTube comments section below. One problem with keeping to a scientific approach to futurism is it can sometimes restrict your thinking on the possible a bit, so it is often good to fish around for thoughts from folks who might be able to think outside the box on a topic a bit easier. However, and I put this as a big warning on this episode and topic in general, many technologies people dream up or write up in science fiction tend to fall apart on inspection from known science, and upon consideration of the implications that they have to have on the plot and narrative. And again, it really is lazy to just say anything is possible, and not too useful either. We study and learn, we find out what is possible, and we occasionally have to alter or even massively overhaul our thinking on that. Knowing how the real science and math works, knowing what we do know, is invaluable. I don't think I need to try hard to convince anyone of that here. It's also something our friends at Brilliant excel at explaining, with practical courses, quizzes, and daily problems on topics like heat and thermodynamics that make the topics far more intuitive to learn. Learning more math and science is hard, but incredibly beneficial in virtually every aspect of life, including just the joy of understanding the world around us better. And places like Brilliant make that learning far easier by presenting topics in easy-to-learn and interactive ways that let you learn easier and at your own pace. A lot of the technologies we discussed today are restricted by thermodynamics, for instance, and we discussed it a lot on the channel as a major limitation on what we can do, but it can often be unclear to folks why it is such a restraint. And Brilliant's Science Essentials course is a great way to learn about thermodynamics and demystify that topic. In addition to many great courses, they have an online community to help you and discuss material with, and fun daily problems that help to exercise your mind and encourage you to challenge yourself every day. If you'd like to learn more science and math, go to brilliant.org/Isaac Arthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can view all the daily problems in the archives and unlock every course. Before we get to the schedule, I just wanted to announce that the upgrades on our website, isaacarthur.net, are complete, and we've added some features like a catalog of all the various books I've recommended over the years, and a new forum, as an additional place you can discuss the concepts and ideas we look at here. And while you're there, you can take a look at some SFIA merchandise we have available. Next week we'll be returning to the Civilizations at the End of Time series to take a look at how civilizations might survive around the deaths of their own suns, and explore some extreme options like living on white dwarfs or converting neutron stars into giant computers, as well as the supernova engine, one of those extreme types of technology we so enjoy here on SFIA. The week after that, we'll return to the Generation Ship series for an equally extreme style of ship, moving entire planets around as colonization vehicles in planet ships. For alerts when those and other episodes come out, make sure to subscribe to the channel, and if you'd like to support future episodes, you can visit our sponsors or donate to the channel on Patreon. Until next time, thanks for watching and have a great week.